Hi there, folks. This is Heath. I'm here from an undisclosed location today um, to cover the day 7 notes, which are our first day on proofs. Let's go ahead and get started. All right. We're going to go over some definitions here. An axiom is a statement whose truth is accepted without proof. It's something that is so basic that we're going to waive it and say, you do not have to prove this statement. We can use these axioms as premises in an argument. As mathematicians, we have to start somewhere. If we assume nothing, if we assume that no statements are true, then every possible statement has an undisclosed, undifferentiated truth value, and we can't then combine any statements to build anything new. And so we have to start with something that we accept even without proof. And these are called our axioms. A theorem is a mathematical statement that can be proven. And in the process of proving a theorem, we'll go through different steps where we're proving that statements are true along the way to getting to the theorem. Anything that we prove before we get to the main result is called a lemma. A lemma is a statement that is used primarily in the proof of other theorems. It is an intermediate step in a proof of a longer theorem. And for some reason this isn't working. It's not wanting to write. Yeah, it's not writing today. Okay. So we'll muddle through without it. A corollary is a statement that comes after the main result. Sometimes after we have proven the main theorem, we might apply that theorem to show something else is true, to give it a sense of value. This is why this theorem is important and allows us to prove these other things. And the things that come after the main results are called corollaries. So the difference between a theorem and a corollary is whether it's the main result or before or after the main result. So for this class, we're going to start with some axioms about integers. These are the things that you will not be asked to prove, that you can go ahead and cite them and accept them without any kind of proof at all. First one I want to talk about is the closure axiom. This is I can't write with, I can write with a mouse, but not with the tablet. Why is that the case? I don't know. Okay, so I can write with a mouse, but I can't aim with the mouse. Closure axiom. For any pair of integers, if I add them together, I still get an integer. If I multiply them together, I still get an integer. We're not going to require that anybody proves that as a fact. We're going to accept the fact that if I combine integers by addition and multiplication, I still get an integer. It is also true that subtracting two integers gives an integer. But in a little while, we'll talk about subtraction as being adding the inverse of an integer. And that way we won't have to do a separate axiom for subtraction. All right, so the commutative property. Commutative property says that for any pair of integers, if I add them together or multiply them together, the order doesn't matter. A plus B and B plus A are the same result. A times B and B times A are the same result. The associative property says that I can group the terms together in any order. I can do, if I'm adding three integers, A plus B plus C, I can add A plus B first and then add C, or I can add B plus C first and then add A. Same thing with multiplication, that the order that we group them doesn't matter also. Again, these are the things that we're going to accept that you do not have to prove. We're going to accept the existence of the number 0. There is an element 0 in the integers, so that when we add that number to any integer, we get a. A plus 0 always equals a. So, other properties about addition we might have to prove, but we don't have to prove that adding 0 doesn't change the answer, or that multiplying by 1 doesn't change the answer. The additive inverse property says that every integer has a negative, or every negative integer has a positive, but every integer has an inverse associated with it, so that when we add the positive of that integer and the negative of that integer together, they cancel and give me 0. That's not true for multiplication. The multiplicative inverse of 3, for example, is 1/3, and 1/3 is not an integer. And so we only are assuming that addition has inverses. We're not assuming that multiplication has inverses. And the last one is the distributive property, that a times b plus c is equal to a times b plus a times c. That we can add these things together and get what we want. Okay? All right. Check one more thing here. Let's move on. So a direct proof of the statement, for all x and s, p of x implies q of x. When we call it a direct proof, we're going to start by assuming that we have p of x already established. Either p of x is an axiom, or p of x is some other statement whose truth value is being asserted in some other way. And then we are going to conclude then that q of x is true. This is the argument that we learned earlier. It was called modus ponens. This is just modus ponens with a quantifier in front of it. Okay. And we have to do this for all x values, which means we cannot assign a specific value to x. We're going to look at some examples of direct proofs today that involve using even and odd integers. And we're going to use these definitions. An integer n is even if we can write it as 2 times an integer k. And so anytime n is even, we can replace an n with a 2k. And an integer is odd if there exists an integer k such that n is 2k plus 1. So we can replace n and 2k plus 1 in our proofs. Okay. So here's our first example of a proof. We're going to prove that if n is odd, then 3n plus 7 is even. Okay? In your mind, I know you're thinking, well, that's not a hard thing to accept, but we're going to go through the steps of just writing out what a direct proof looks like. Okay? So our first statement here, that's a little too high, says assume that n is an odd integer. That is, we're starting with the assumption that what we have here we're assuming that n is an odd integer has already been established. Okay? It is a propositional function. It can be true, it can be false, depending on the value of n. But we're only interested in the domain for which n is true. So over the set of values for which n is true, we can assume that n is true. Then in the second sentence, we're going to take that assumption and apply the definition to the assumption. Since n is odd, that means n is equal to 2k plus 1 for some integer k. And then we're going to calculate out 3n plus 7 based on that calculation. So this is the third thing we did. 3n plus 7 equals 3 times 2k plus 1 plus 7, which is 6k plus 3 plus 7, which is 6k plus 10, which is 2 times 3k plus 5. Now I see that 2 times and I think, that's an integer. That's an even integer. But we also have to show that what's next to the 2 is an integer. 2 times something that's not an integer might not be even. For example, 2 times 1.5 isn't even. 2 times 1.5 is odd. It's 3. So we have to establish that 3k plus 5 is an integer and not a fraction. But we get that because of the closure axiom. That all we're doing to k is multiplying it by 3 and adding 5, and that was the very first axiom. And so this step 4, the closure axiom, is necessary so that we have this part of the definition right here. If I can find my cursor. That k has to be an integer in order for something to be even or odd based on it. So we're establishing why 3k plus 5 is an integer, and therefore 2 times 3k plus 5 is an even integer. And so at the end, this is step 5. We have finished the proof that we have here. Okay? So I'll talk about these steps in a little bit more detail on the next couple of slides. The first sentence of the proof starts out with assume that, and then we substitute the hypothesis into the blank. Whatever that hypothesis is, in this case n is an odd integer, we're starting with the statement assume that n is an odd integer. That's not optional. All direct proofs have to begin with that step. There are different ways of phrasing it. Sometimes you will see the word suppose instead of assume. But we have to assume that the hypothesis has already been established is true. And so we write that assumption out somehow. And again, we can change the wording, but we can't leave out the step of asserting that the hypothesis has already been shown to be true. So all direct proofs begin with this step. If I ask you to prove something by direct proof, no matter how difficult the proof is, you should always be able to write out the first sentence because it's an automatic thing. Okay? The second sentence in the proof takes what we did in the first sentence and applies a definition to it. It says, okay, now that we have assumed that something is true, what does that mean? Since n is odd, we can change that n to 2k plus 1. And then we can make use of that 2k plus 1 to figure out something about 3n plus 7. So the second sentence of the proof applies a definition to the hypothesis. It takes that hypothesis and finds something to work with. As the proofs get more complicated, you may have several definitions that you can apply in the second step. And part of the process of writing a good proof will be deciding which of those definitions is relevant and which ones aren't. In this case, there's only one, and so we just go ahead and use it. Most direct proofs will include one or more steps like this. Start applying some definitions to the things in the proof until we can find something we can use. The last sentence of the proof, finish up with our conclusion. So blank. And then we substitute the conclusions into blank. If I go back here, we ended up with so 3n plus 7 is an even integer. That was a terrible line. That's better. There we go. 3n plus 7 is an even integer. That's what we concluded with. We assumed the p of x part was true. We finished by showing that the q of x part was true. Now, again, there are different ways you can phrase it. Sometimes you'll say therefore instead of so, or thus, or hence. Sometimes we just say we can conclude such and such is true. Direct proofs always end with this step. That first sentence and that last sentence, starting with that assumption p of x, showing that it leads to q of x. If you leave one of those out, your proof is incomplete. You have to have that starting and ending statement. You are free to rephrase it a little bit, but you have to include it. And then oftentimes when you're writing a proof in a larger context, in a book or something, there's this little symbol here at the end that lets the reader know that this is the end of the proof, and then there's more text that comes on after this. That symbol doesn't have to appear in all contexts, but if the text continues and you want to separate the proof from the text, you have to have some kind of indicator to the reader that says, we're now transitioning back away from writing a proof to doing some other kind of writing. Okay? Modern textbooks a lot of times use some kind of like a filled-in circle or filled-in square. Older textbooks that were printed using movable type often use the Latin abbreviation QED, which stands for "So we proved it," quote or demonstrated. So we demonstrated it. All right. This is clearly not a proof. It's missing some of those things. Proof that n is an odd integer, then 3n plus 7 is an even integer. So let's let n be 5, then it's an odd integer. So 3n plus 7 is 22, and 22 is an even integer, so we're done. Don't do that. First of all, you're only doing this for one element in the domain. You're only showing this as for n equals 5. You're not using the property of being odd, you're just using 5. And it's missing the opening statement, it's missing the closing statement, it's missing the structure of the direct proof also. This is a terrible not a proof. It is, this terrible not a proof barely works. Okay? This fails to be a proof because only a single example is checked and not the infinite number of other possible odd integers. Example is never ever a proof of a statement with a universal quantifier, but sometimes working through a few examples as scratch work gives us some insight in how to construct a proof. As the proofs get harder, and we start talking about some of these harder proofs, you'll see me work through an example first before we get to the idea of like, well, here's what the pattern is. No matter which odd integer we pick, we always get to this intermediate step. So let's focus on that. Examples can help us write a proof, but they can't be proofs themselves. All right. So let's look at another example of a proof. Prove that if n is even, then 3n to the 5th is even. So if n is an even integer, then 3n to the 5th is an even integer. So again, we're going to look at the different parts. The first sentence is assume that, and then we restate the hypothesis. Assume that n is an even integer. Again, you can rephrase this, but you can't omit this. You can't leave this out. Since n is even, we can write n equals 2k for some integer k. That's the second sentence. Take what we just assumed and find a definition or a previous result or something that we know about even integers that we can apply to complete this proof. Then, and now I'm going to do some algebra, do some calculations using the piece of information we covered in the second step. So 3n plus 5 is the same as 3 times 2 to the k, 2k to the 5th, which is work all this out, 2 times 48k to the 5th. Now, this looks like it's even, but again, to be a complete proof, we have to assert that 48k to the 5th is an integer, because if it's a fraction, 2 times a fraction might not be even. So 48k to the 5th is an integer because of that closure axiom. And since 48k to the 5th is an even integer, 2 times 48k to the 5th is an even integer. And so, let me say that again because I may have said it wrong. 48k to the 5th is an integer, and so 2 times 48k to the 5th is an even integer. And therefore, 3 into the 5th is an even integer, and that finishes the proof. And this time I used an open square instead of a closed square to end the proof, and that's okay. On a slide, it's not necessary because this is the end of the text on the slide, but in printed notes, I might want to use some kind of indication that when we go on, we're moving on to something else. Okay? All right. So let's try this example. This example is blank. Let's work through this. Proves that if the sum of 2 integers is even, then their difference is also even. Okay? So we are without the drawing tablet today, but I will try to do this. So we're going to begin with our assumption statement. Assume that the sum of 2 integers is even. 2 integers is even. Okay? Well, I would like to be able to talk about these 2 integers. So, well, we need some letters to describe these integers. So assume that the sum of 2 integers are even. So what we might modify this is to give these integers a name. Say a plus b. So parenthetically, I am giving these 2 integers names. And now I can apply a definition. Then a plus b equals 2k, where k is an integer. So then how do we get from a plus b to a minus b? So I need to do some calculations here. A minus b is a plus b minus 2b. It's the same as adding b and then subtracting 2b. And so a plus b is 2k. And that's the same thing as 2 times k minus b. Now, normally at this point, we say, since k is an integer, by the closure axiom, 2 times k is an integer. But there are 2 integers here, so we have to be careful. We have to say, since k and b are integers, by the closure axiom, k minus b is an integer. Or even better yet, k plus negative b. Because the closure axiom only applies to addition, but we have an inverse axiom as well. So k plus minus b is an integer. All right. Therefore, when we multiply an integer by 2, 2 times k minus b is an even integer. And now we get to finish our proof. We assume that the sum of 2 integers, a plus b, is even. We have now shown that their difference 2 times k minus b is also even. So their difference is also even. I am starting with the premise, the hypothesis, and I'm ending with the conclusion. And I'm following this structure of applying some definition to the hypothesis, then using that definition in some sort of computations or some kind of reasoning, and then taking what we've got and applying usually the closure axiom, but it could be something else, to get to a definition that gets me to the final result, which we stated at the very end. Okay? There's just a pattern to this. The more comfortable you get with that pattern, the easier it is to write out some correct proofs. All right, let's move on. All right. If you're working this at home, pause the video for a moment and try to write out this proof yourself. I'm going to go ahead and continue on to do this, but it's very similar to one of the examples we did earlier. Proof that if n is an even integer, then 5n minus 3 is an odd integer. So we're going to start with an assumption, assume that n is an even integer. Then apply a definition. Then n equals 2k, where k is an integer. Then, now we're going to work out some calculations. Negative 5n minus 3 is negative 5 times 2k minus 3, which is negative 10k plus 15, which is equal to 2 times negative k plus 7, sorry, negative 5k plus 7, plus 1. 2 times negative 5 gives me negative 10k, 2 times 7 gives me 14, plus 1 gives me 15. I want to get this in the form 2 times something plus 1. I have that now. State what we need to be able to conclude that this is odd is that what's in parentheses there is a whole number. It's an integer. So by the closure axiom, negative 5k plus 7 is an integer. And so 2 times negative 5k plus 7 plus 1 is an odd integer. Therefore, or so, doesn't matter. So negative 5n minus 3 is an odd integer. All right, so today we've just been working with odd and even integers. We're not going to be working just with odd and even integers. What we're going to look at on Monday is other kinds of things that we can prove using direct proof. Statements about prime numbers, statements about rational versus irrational numbers, some of these other things we can handle. So what we're looking at today is just getting some practice building the correct structure for these proofs with a very limited set of definitions, just a definition of odd and a definition of even. And starting on Monday, we're going to throw some more definitions, prime and rational and some of these other things, and see how they work as well. All right? So thank you for coming. I appreciate you putting up with the late video. I'm sorry for the technical trouble at home.